exercises, and we'll perhaps manage them for today, but I'll try to go through at least some of them. So, first of all, exercise 3 from chapter 3, and this is both an example of a classical setting within statistics where you have two groups that you want to compare. But at the same time, it's also an example where we can use building blocks or use previous results to build blocks together. And also we will see that there is a lot of independent structure that we also can utilize. But the setting then is that we have data from two different groups. 32 observations within the first one and 6 from the second. And for both groups, we are going to assume that we have a Gaussian set of observations. And in addition, we will then use conjugate priors, which then means that a lot of the mathematics will simplify. But first of all, now, given that we assume that we have data that are Gaussian and also that they are independent between the different groups, then we have seen that for Gaussian data, the sufficient statistics are the sample mean and the sample variance or sample standard deviation. So that means that when we in the exercise only are provided with these summary statistics, we still can perform a full Bayesian or likelihood-based analysis due to that all the information that we need are given through these two measures. So that's the first thing to notice. But then we are going to look at a Bayesian analysis on this. And in the end, we are interested in saying something about the difference between the expectations between the two groups. So that's the parameter of interest. But note that in order to do this analysis based on the Gaussian distribution, we need some extra nuisance parameters. So the variances in each group can be considered some nuisance. We are not particularly interested in them, but we need to consider them in order to take properly into account uncertainty related to estimation of that one as well. But what we are going to do then is to assume a uniform prior on then all the parameters involved. But note that then for the variances or standard deviations, assume that this uniform prior on the log scale. So, and also note that perhaps I should go through this because that might have been a bit unclear to say well. But, so we assume then the prior for all the control group, the log sigma c, and mu, and then what's called other group, treatments, sigma treatments, proportional to 1, that actually imply that we also have that they are independent. And so on. So, and in particular then, that if you look at then this one of these standard deviation, that has a prior proportional to 1. But if you now call this another parameter tau, then that means that we also could say that tau has a prior proportional to 1. But then we can go back and say, well, what is then the prior for this? Perhaps I should write the C here. what is then the prime for the variance itself? Well, but then we can use the transformation rule in that we have sigma c is equal to well, sigma c squared is 1/2 exponential of c, like that. But then we can utilize then just the transformation rule, and that in order to get then the distribution for sigma c squared, we can insert it into the distribution for tau, which is just okay, to the proportionalities is just this one. But then we have to take the derivative of the transformation, and so should rather tau c can also be written as 1/2 log sigma c squared. And if I take the derivative of that, I get 1/2 sigma squared. And this is then proportional to sigma c to the power -2. So this means that when we actually are assuming a uniform prior on the log scale of the standard deviation, that corresponds to a prior 1/sigma squared on the original scale. So, so this is then the actual prior that we are using. Okay, but this is actually then a setting that we have discussed earlier through the lecture, where we have then this conjugate type of prior, and where we actually then derived the marginal distribution for the for mu, for the expectation. So and what we ended up with in that case was actually that the prior that the posterior was then t distributed. So we can actually, even though now we have two sets of parameters and two sets of observations, due to the independent structure in the prior and the independent structure in the data, the posteriors also become independent. So perhaps I should write this as well. So since p of mu c log p of mu c sigma c squared t sigma t squared can be written as p of mu c sigma c squared times the prior for the treatment group. So we have independence there, and furthermore we have that the data y, if we say yc is the data from the control group, and yt is the data from the treatment group, given all the parameters. Then that one also is, has the independent structure. Well, those two together imply then that we also get independence in the posterior. So if we now look at the posterior of c sigma c squared t sigma t squared, well, that is proportional to the prior. Then that is proportional to the prior, which we could write c sigma c squared t sigma t squared times then the likelihood, which could be factorized into one term only involving the control group and one term only involving the treatment group. Then we see that this also is proportional then to the product of the posteriors. So we have independence also in the posterior, and that then helps us considerable, because then we can look at these two groups separately, and within each group we are in exactly the same setting as we have discussed earlier. We have Gaussian data, we have conjugate priors, and then we directly then have that the posterior or the marginal posterior from U, C, is t distributed, and similarly for the treatment group. So by utilizing then these simple settings that we have considered earlier, we can now look at more complex settings. It's not very much complex now, but we will see them later on today that we actually can use this also in more complex settings. Okay, so this means that we actually can both obtain the marginal distributions for the two different expectations. We actually also have the simultaneous distribution because they are independent. So the simultaneous is just the product of these two distributions. But now comes a bit more complicated part, and that is due to that what we are interested in is the difference between these two parameters, mu c and mu t. And that is not that easy to derive, the distribution of, if you now are interested in P of the distribution of mu c minus mu t given data. And then we have to consider both data sets. Well, it will be one can write it down as an integral with respect to both the t distributions, but it can be quite complicated to do that kind of calculations. And that's where now simulation comes to the rescue, because it's very simple to simulate the difference. The only thing we need to do is then to start by simulating a set of mu values from the posterior distribution of mu c in the control group. And that is just by simulating a lot of t distributed variables. And there's a routine in R called RT which does this for us. And note that this RT distribution in R assumes an expectation of 0 and a scale parameter of 1, which means that we have to add the expectation and we have to multiply by the scale. These are the values that we have up here. So we can do that for the control group, and we can do similarly for the treatment group. And then we can just take the difference between all these simulated values. And when we have the differences, we can extract different types of features. We can make a histogram, so we get some kind of feeling on how this difference looks like. And just by looking at the histogram, we see then that the main part of this histogram is above 0, which indicates that there really is a difference between these two means. And we can also extract then all the kind of summaries. So we can make a posterior interval. So including constructing interval where it is 95% certain that the parameter is within that interval. And this we can obtain by just taking quantiles, empirical quantiles within these 1,000 simulations. So this can be obtained by sorting first and then taking the 25th observation and then the below and the similar at the tail. And then we obtain an interval that goes from 0.05 to 0.27, which again is different from, it does not include 0, which means that we are quite certain that, that the difference is different from 0. So we actually do get an increase, and whether that is an improvement or not, I don't remember the text there, but let's hope that that's it. Okay, so that's exercise. Any questions to that? Right, next exercise was exercise 7. Now that's turned out to be a bit strange, because, at least for me, because I was not able to show this. Was any of you able to do that? Right, so it might be that there is an error in that exercise, because if you try to do actually that I at least got that these likelihoods are different. So the point here was that we could look at both B and B as independent Poisson, and then we would get the likelihood. But then we could, in some sense, condition on the total number and look at the binomial distribution. But I think what is wrong here is that we then don't take into account that also B plus B is stochastic. So if you multiply by a Poisson distribution for the sum, which follows in some sense from that they are independent Poisson, then you would get the same likelihood. But that is not what they asked for. So so it's a bit so it was a bit unfortunate that I actually gave this exercise. Okay, but then let's move on. So we did have right. So the last two exercises from this chapter was then mainly to derive then some equations or formulas that were given in the book. But given then that also there are quite detailed solutions provided for this, I was not planning to go through this, but if you have questions to those, please go on. So it's mainly to do some kind of manipulations then on this posterior distribution for the univariate case, and then also there's well, actually. Yeah, you might have seen this, that there is one link to solutions which is provided by the authors of the book, but then I also made a separate document where some of the exercises that do not have solutions from the authors, where I'm giving them some suggested solutions. And it's mainly that to manipulate these series in the right way. So important that you go through them, but it's mainly help this type of exercise. Okay, but then we also then have some exercises, some exam exercises. So, so this is then from 2020. So here again, we consider an Gaussian setting. So we have observations Y that are Gaussian, and we are then supposed to find the Jeffreys prime. So that the Jeffreys prior is given then by the expected Fisher information matrix, or the determinant of that, to the power of a half. So that means that in order to calculate the Jeffreys prior, then we need to calculate all these second derivatives and take the expectation of that. There is a solution then also available there, which essentially is doing this. So first of all, we need to look at the log density, and then do the calculations of the derivatives. So we then get that the expected and the derivatives is then displayed as a matrix here. And then we need to take the expectation of that, and we see that the diagonal, well, the first term doesn't depend on the data at all, so then the expectation is itself. If you look at this off-diagonal term, then the expectation of mu, or of y is mu, so then we can just get mu minus mu, so we get the 0. And then for the last term, we have y minus mu to the power of 2. And the expectation of that is sigma squared, and then it should be divided by sigma, sigma to the power of 6, so we get an expression of 1 over sigma to the power of 4.
Excuse me?
Yes?
So in that exam text, looks like the expectation is over the parameter, since there's a theta in there. Why is that?
Sorry?
If you look in the text in the exam,
You mean this theta?
No, on the exam question.
The actual exam text.
So there it looks like when you look at the definition of the Fisher information,
Yeah.
so it looks like the expectation is over the theta.
Well, yeah, so that might be a bit unfortunate if you're not used to this kind of notation, but usually one writes when one wants to say that one takes the expectation given a specific parameter set, one typically puts it as an index down there.
Okay.
While if one would like to emphasize what is the stochastic part, one typically uses it as a super index. So, so if one really would like to write this properly, one should write expectation like that. So this means that the random part is this, and this is in substance what is fixed. So in the what kind of setting you are, but it might have been a bit confusing actually to include that at all. But the expectation is with respect to the observations. Okay, so that means that then we get that this information matrix is just a diagonal matrix, which means that the determinant can be easily found by just taking the product of the diagonal terms. And then we get Jeffreys priors by just taking the square root of this, which then becomes sigma to the power of minus 3. So this is then a somewhat different type of prior compared to when we in the first exercise of the day, then we said that we would have a uniform prior on log sigma, and we ended up with a prior for sigma squared by 1 over sigma squared. So now we have a somewhat different 1 over sigma to the power of 3. So depending on different types of principles one are using to describe to construct priors, one also obtain different types. And there are different reasons for choosing the different things. Okay, but given now then this, we now want to derive then the posterior distribution for the parameters mu and sigma squared, given the observations. And then one has, in principle, to go through the standard type of calculations, in that the posterior will be then proportional to the prior, which is sigma to the power of minus 3. multiplied by the likelihood, which then is the rest here, sigma to the power of minus n, and then we have the exponential of this expression, which we perhaps remember from the lectures. And then one can just go through the same kind of calculations as we did earlier. The only difference that we have now is that we have minus n minus 3 instead of minus n minus 2 that we had earlier. And this then results in that when we come to the well, first of all, the distribution for mu given sigma squared doesn't change at all. So that is exactly the same as before. But the posterior distribution for sigma squared is somewhat different in that now we get that that this first parameter in the inverse gamma distribution, inverse chi-square distribution, is n instead of n minus 1. So we in some sense gain somewhat 1 degree of freedom by changing then this prior. And this prior can be considered as somewhat more informative than the one that we have. So that's then is exercise B. Then we are going to consider this setting of loss functions. So assume now that we make a quadratic loss function, either for mu or for sigma squared. We are then going to find the base estimator. And the base estimator is then the one that minimizes the expected loss. But then we can build on that we already have gone through last week, in that if we have quadratic loss, then the optimal decision or the base estimator is the posterior expectation. So what we need to do then in order to find this base estimator is to find the conditional expectation of mu and the conditional expectation of sigma squared. And then let's have a look on this. Well, if we first now look at the expectation of mu given the data. Well, now we don't really have this directly in what we have found so far. But note that we can write this as the expectation of mu given sigma squared and y, like this, using then this rule about double expectation. And this conditional expectation, where we also conditional sigma squared, well, that we have already found. That's the expectation in this Gaussian distribution. So that is y bar. But then we have to take the expectation again, but now note that given y, then also y bar is given. So there's nothing more stochastic there. So this then just becomes y bar. So the base estimator in this case will then just be the average of the observations. Okay, but then we also need to look at the expectation of sigma squared given the data. But here we then do have directly, in some sense, the results, due to that we have found now that the marginal distribution of sigma squared given y is inverse chi-squared. And then we can go back in the table in the appendix A to see what is the expectation in this inverse chi-square distribution. Well, that's the degrees of freedom, which is n divided by n minus 2 times this scaling factor s squared. So that we can also get directly down from this table. So then we do have then the results. note that this then is somewhat different from what we would have if we had chosen this alternative prior, and that now we get earlier we would have if we had used a prior of sigma squared to be 1 over sigma squared, then we would have that the posterior would be inverse chi squared with n minus 1 s squared, and we would have that the expectation would be then n minus 1 divided by n minus 3 s squared. So somewhat different, but when n is large, then this will not make much difference. Okay, and then we had a final question. That was then to consider a somewhat different loss function. So here we say that, well, if we are able to get an estimate theta hat within a distance epsilon from the true parameter, well, then we say that we don't have any loss. Well, if we are missing that with this epsilon deviation, then we have a loss of 1. So kind of strange type of loss function, but in some sense emphasizing that now we are really trying to target a true value, and if we don't really get a true value, then everything is bad in some sense. And but the point then with this exercise is that first of all to see, well, can we derive then the base estimator, and we can do that by then using the definition of the expected loss. So if you then look at the expected loss, well, then this loss function can also be written as the indicator function of the distance between theta and theta hat being larger than epsilon. And when we then want to have the expected loss, we take the integral of this with respect to the parameter or the posterior distribution for the parameter. And then we see that this is equal to, so we only get a contribution outside epsilon. So this would then actually be 1 minus the probability that theta, the distance between theta and theta is less or equal to epsilon. Okay, so this is then the expected loss, but then the task is to try to find out, well, which theta hat will give this, will minimize this expected loss. Well, we will minimize this if we are able to maximize this probability. But if we then think about it, then perhaps it would be easy to draw. Let's say that we have a distribution that is perhaps something like this. So, and we are looking at very small intervals. But then, the probability then will be an integral over these small intervals. But then, of course, the integral over these small intervals will be highest if we pick the highest points in the distribution. So that means that we should choose theta hat at or close to the mode of this posterior. And if we now put epsilon less smaller and smaller, we will get closer and closer to the actual mode. So this actually then shows that this type of loss function, where we penalize all kind of errors that we make, actually corresponds to choosing the mode in the posterior distribution. And the mode might be a sensible thing to choose if we just think more about it without relating it to loss functions. But at the same time, it does correspond to a quite strange type of loss functions. So we should keep that. Questions there?
I have a
Yeah.
for the former. You said if you have a quadratic loss function, then the optimal solution will be an expected base posterior. What did you say?
If you have a quadratic loss
Yes.
function, the optimal estimator of decision is the posterior expectation.
Posterior expectation.
Yes.
What if you have a non-quadratic or something similar? Is there any
Well,
area?
we went through that last week, but that
Okay.
if you, instance, have an absolute value type of loss function, then you can also derive analytically that you have the median. But in more complex settings, it might be difficult to get analytical results, and then you would have to do some kind of numerical calculations in order to derive.
Yes.
So does that mean that when you do this decision theory thing, so you end up with this, so you use quadratic instead of most, just because it's easy to calculate when you choose loss function for doing decision theory, so you end up with the expectation instead of the most? Is that just a
Well,
mathematical?
well, first of all, now when we go through this clear blind base, we do for convenience choose a lot of easy loss functions in order to derive mathematical results. But in a realistic setting, you should really think about what kind of loss function you believe in. And it might, for instance, be so we did discuss then two loss functions last time. So we had this quadratic one. We had this absolute value. But it might be that, for instance, something like this would be more easy. In that, if you are, you might say that the difference between an error of 1 and 2 is it's much worse with 2 than 1. But it might not be much worse to miss with 1,000 compared to 10,000. It's so far away anyway that it doesn't matter. And that would correspond to that this loss function would flatten out when you have too large errors. So that so it depends a bit on the setting that you are interested in. That said, again, one should never only report this point estimate. Given now that all that we have this Bayesian paradigm saying that the posterior distribution contains all the information that we want, you should always also include the full posterior distribution, because then you are able to say a bit more than just this point estimate. So, but if you really need to make a decision, then you should consider that. You can think of this COVID-19 setting where you want to estimate this reproduction number. It might be much worse if you underestimate it. If it is larger than 1, then you will have an explosion in the number of individuals infected. If it's below 1, then you are in control. So it's much worse from a health type of setting to underestimate it if it's larger than 1 compared to the other. So in that case, it might be that you would have perhaps something like this, and then that it goes up, continues to go up on the other side. So depends on the situation. Okay. exercise 2. So let's see if I can find that one as well. Right, so this is then a somewhat different distribution from what we have been looking at so far. This is the Weibull distribution, which is a popular distribution to use when you look at durations until something happens, for instance, lifetime data. And this has then this specific form. Just for simplicity in exercise, we assume that theta is known, so the only unknown parameter is sigma, and sigma is a scale parameter in this model. But the first thing then is to actually rewrite then this distribution. Then it is expressed with a reparameterization of sigma. So we write tau instead of use tau instead of sigma, but tau is then sigma to the power of minus theta. And this is and the exercise here is just to rewrite this distribution then with expressed with tau. But then we see that this 1 over sigma theta is exactly equal to tau, so we get theta times tau instead, and then also we see that we have 1 over sigma theta within the exponential function here, so we get the exponential of minus y to the power of theta times tau. And then we are supposed to show them that the gamma distribution is a conjugate family here, and that we might already see here that we have tau to the power of something, and then we have the exponential of minus tau times something. And this is exactly the shape that also the gamma distribution has. So it's reasonable to consider then that kind of prior. And if we do that, so and look then at the posterior, then the usual trick is that we look at the prior times the likelihood. And the prior then is proportional to this tau to the now power of the parameter in our gamma prior, which is we have chosen to be a and b here. So tau to the power of a minus 1, a to the power of minus tau, and then we have the likelihood. And then when we go through this, then we get exactly a new gamma distribution, but then with the parameters updated. And then we can use the transformation rule to go back to sigma and obtain that then this posterior for sigma will then be a gamma density times then this part that comes from the transformation. And then the second part of this exercise was then to calculate the third part was then to calculate the marginal distribution, and it's actually a typo here. The first thing to go here, that it should be a p. The prior for tau should be included within it. And then if you insert that and then go through the calculations, you end up with an expression like this. So, actually, this is quite similar to what we have looked at earlier. Okay, so then we have been through most of the exercises. There are 2 exercises left from chapter 4. Now, but I think it's time for a break, so let's take